So I wanted to do a quick walkthrough of the final exam review document for Algebra 2. So let's jump right into it. So number 1 here, we are simplifying a fraction. So that's where we want to cancel factors. So you do have to factor first sometimes so that you can then cancel the factors, and whatever's left is your answer. Looking at number 2, it's the same kind of thing, just we don't have binomial factors, we just have variables here. So remember, you multiply fractions straight across. So if you multiply across here, 2 times 3 is how I got that 6. And then you add the exponents. That's what it says over here. You add the exponents when you multiply. So 2 plus 3 gave me the 5. This one came over here. 9 times 14. So I didn't actually work that out for a reason you'll see here in a second. X to the third times x to the first. 3 plus 1 is 4, and then we had a y on the bottom. Now, when you divide powers, you subtract the exponents. So, for example, 5 minus 1 is how I got the 4 on the y, and 5 minus 4 is how I got the 1 on the x. Now, where in the world did this 1 over 21 come from? Well, if you come down here and look at this, I've just copied those numbers. Now, I went ahead and factored those. 6 is the same thing as 2 times 3. 9 is the same thing as 3 times 3. 14 is the same as 2 times 7. And then I could cancel factors that match. So you see the 3's cancel and the 2's cancel, leaving a 3 and a 7 all in the denominator. So that's where that 1 over 21 came from, which could also be written this way as a fraction for your answer. Number 3, when you divide fractions, you have to remember to keep change flips. So you change it to multiplication and you flip over that second one. Now, as I was writing it, I was factoring. So the 4x plus 2 is the same thing as this right here. And then x squared minus 9 is the same thing as x plus 3, x minus 3. Over here I factored, took out a greatest common factor, and this was one of those more difficult reverse FOIL ones where it does factor. And then I simply canceled the factors that match, those two match, and then the 2x plus 1 also match. So anything that's left is part of your answer, which is what I have there. Now, to add fractions, you need a common denominator, and you could see that these denominators are not the same. So we're going to upgrade each fraction so that they match. So what would the common denominator between 5 and x be? It would be 5x. So we came up with a plan to make that happen. In order to turn this into 5x, it would need to be multiplied by 5 over 5. It has to be something over itself. In order to turn 5 into 5x, you have to multiply by x over x. Now, whatever happens on the top happens. So 5 times 3 is 15. X times x is x squared. X squared plus 15 is what you get on the top because you add the numerators. But remember, the denominator stays the same when you add fractions. Same thing when you subtract fractions. The denominator will stay the same once we get there. So I rewrote the problem in black here, leaving myself a little room because I knew I needed to introduce missing factors. So on the first one, we had an x plus 5. I needed to introduce this x minus 2. So x minus 2 over itself is in red there. And then this fraction here did not have the x plus 5. So I introduced it on the top and bottom. Now this is going to have to be distributed. And that's what I did right there throughout this entire problem. Don't lose the minus sign. And then I had to distribute this as well, and I had to distribute the minus sign. Here's the danger zone where I would see some students have a problem. Don't forget to distribute that minus sign on the 5 and get negative 15. I then combined like terms, and that's where I got that numerator. 4 minus 3x is 1x minus 23, and the denominator stays the same. Solving rational equations, off to the side, I put the strategy. The strategy is to get all the denominators to be the same, and then you just throw away the denominator and solve the numerator equation, and don't forget to watch for those extraneous solutions. So what are extraneous solutions? So let's just jump right in and talk about that. Here in the original problem, we have the factor x and the factor x plus 2. So that is never allowed to be 0 because it would cause a divide by 0 error. So as we're about to solve this, we're kind of keeping a keen eye out that x can never be 0 and x can never be negative 2. So I upgraded all the fractions, just like in number 5, so that all the denominators became the same. I then rewrote the numerator equation by foiling things out, or the distributive property, whatever it takes. Okay, and I threw away the denominator temporarily. I then got all the x's to one side, and I was able to find the answer. I think the answer is 3. Well, the answer 3 is not in the list of my problem children over here, the extraneous solution concerns. So I went ahead and put a box around this and said, yep, that's my answer. Vertical and horizontal asymptotes. Vertical asymptotes are easy. Vertical asymptotes happen when there's a problem in the domain, some x that it is not allowed to be. So you set the denominator equal to 0 and you say, you know what, x is never allowed to be negative 5. But don't forget that if that factor happened to have another x plus 5 hiding in the numerator, then it would have been a whole and not an asymptote. So I said right here, this, since there's no x plus 5 factor in the numerator to cancel that thing, x equals negative 5 is indeed a problem, and it causes a vertical asymptote in the graph. All right, what about horizontal? This is where you have to imagine plugging infinity in. So I've written the fancy schmancy limit notation here. As x approaches infinity, what is this fraction behaving like? Well, it's going to look a lot like 2 infinity over infinity. The infinities would cancel, so this thing is approaching 2 is what we say. This function up here is approximately 2 as the numbers get really big. That's the definition of a horizontal asymptote. As we go way to the right or way to the left, what are we approaching? We are approaching the number 2, so that is a horizontal asymptote. Number 8 deals with what are called composite functions, where you are putting one function inside another and you're creating a new function. So in part A, it says find f composed of g. F composed of g. I like to write it this way, f of g, where you're putting g, here's g, we're putting it inside f. Remember, f is something minus 3. So we put that in there, we can then simplify, we get 2x squared minus 7. Now in reverse, we can find g of f, where we take the g function. Remember, the g function is 2 times the square of the input minus 4. So I put the f function in there. Now be careful, I've seen a lot of students mess this up. You cannot distribute the 2. Why not? Because you have to do exponents first. Remember PEMDAS, please excuse my dear Aunt Sally. If we have to square this first, so we get x minus 3, and we FOIL that out. Now you can safely distribute the 2. Now that you've done the squaring, you can distribute the 2 and combine like terms, and you get your polynomial answer down here. That's our new function. All right, finding inverses is really easy. Here's the steps over here. You take the original function and you switch the x and y. Okay, so here's the original function, and then you see how the y became x and the x became y. That's what I mean by switching the x and y's. And then you just simply use your algebra and you solve for y. So I'm going to add 2, so it gets to the other side, right? Then we have this here. And then to get rid of the third, you multiply by 3. So there's the inverse function. So then I rewrote it in inverse, the proper inverse notation here. G with the little -1 up there means the inverse of g. Okay, let's keep moving along here. How do we verify that 2 functions are inverses? Are the 2 functions inverses? What you do is you do f of g and you do g of f, and they both, you have to do it both ways here, they both come out to be x. Well, if that happens, then you can say a big fat yes. And you see, I showed my work. You have to actually show your work on these to show the proof. It's almost like a geometric proof. This is an algebraic proof that indeed these are inverses, and they do come out to be, because when you square a square root, you just get the stuff inside. When you square root a square, you just get the stuff inside. All right, moving on. Number 11. Is this growth or decay? All right, so if the base is bigger than 1, it's growth. If that had been a decimal, like 0.8, then it would be decay. Number 12, condensing and expanding logarithms. So the properties of logarithms, and I posted a really good video on these properties, actually 2 videos, so you can go through and really get a good review on those logarithms. If you have the multiplication inside one log, it splits into 2 separate logs. Notice how I've written the word log twice with a plus sign in the middle. If you're dividing a divided by b inside one log, it splits into 2 separate logs. Again, the word log is written twice, and it becomes a minus. And then any exponent can be thrown out front of a logarithm. There's also this handy change of base formula, and this is how you're able to put it in the calculator if you're using one of my cheaper calculators. To find the log base a of b, you have to put log b on top divided by log of a. And make sure you close this parenthesis on the calculator. And remember, the base is down low, so you can remember that it's down low on the fraction. So here we have a question where they're saying, condense this, put it back together again. We have multiple logs, so we can combine them into one log. And anytime you have a positive log, it is multiplication on the top. So x plus y would equal x times y inside one logarithm. You see how I'm using that property there? This logarithm is negative, so whenever you have a negative logarithm, it goes on the bottom of the fraction on the inside of the logarithm. On letter B, we have an exponent out front, so that's going to be thrown up top. We have a coefficient out front, so that's going to be thrown up top as an exponent. So that's why I got 2 to the third. It's on the bottom because it was negative, right? So that means division inside a log. Notice the base is 4 here, so I wrote that there. 2 to the third power is not 6. By the way, it is 8. So I went ahead and rewrote the problem nicely there. Now, logarithms are really handy because you can solve exponential equations. 2 to the what power is 8. Now, we know the answer is 3, but you can convert to exponential form, or convert exponential form into log form, and here's how you do that. Remember, the base is the base. Answers to logs are exponents, and then that must mean the 8 goes inside the log. So that's log form. Then you could type in the calculator log 8 divided by log 2, or 2 to the what power is 8? It's 3. Now, in the second question, we end up getting a decimal answer. So we're given exponential form, and the base is the base. I'm rewriting it in log form now. Answers to logs are exponents, so that one over there. And then the answer to the exponential goes inside the log. Now, this is just a decimal, right? You would type this in your calculator, and you could just get the decimal. I use the change of base formula. After you get the decimal, you would add 1 to both sides, and then divide by 3. So if you want to be really efficient, you could just type this whole thing in your calculator very carefully in one shot. Now in letter C, we're going to actually solve what's called a logarithmic equation by writing the exponential. So again, we're going to convert form. So we've been given log form, we're going to convert to exponential form. The base is the base. Answers to logs, so that's over here, are exponents in exponential form, and this stuff over here goes on the right side in exponential form. 3 squared is 9. That's easy. We add 12 to both sides to get rid of that negative 12, and then just divide by 7. X equals 3 is the answer. We are really close to being done here. We also talked about exponential growth and decay, including compounding. So here's the way you set up a decay problem. You put a minus in here. Remember, this number in the front is always your starting amount. This is the rate of change, and then your time goes up there. So in this question, it says an 8.7%. So that's 0.087 when you convert it to a decimal. Since it's going down, it's declining, that's why I'm using a minus sign in our formula. 50 comes from 2030 minus 1980. That's 50 years. And we type that in, we get just under 2,000 teachers. Now, number 15, this is compounded quarterly. So we have to use a little bit different of a formula. Quarterly means n is 4. Remember, if it's daily, n would be 365. If it's semi-annually, n would be 2. If it's weekly, n would be 52, and so on. So these are just facts that you should be able to just remember. All right, so I set this up. This is the amount we're depositing. 1 plus, because it is growing. It is growing this time, so I'm putting plus there. And then you change your interest rate by moving the decimal twice or dividing by 100, all over n equals 4, and it says 12 years. So I went ahead and typed this very carefully in the calculator, and there's my answer. All right, let's finish this up with the last stuff we talked about, are conics. And this would be, we started with the midpoint formula. Let me start down here with midpoint. Midpoint is where you just add them up and divide by 2, the x-coordinates, and you find the mean or average of the y's. Just add them up, divide by 2. Now the distance formula between 2 points is written over here. You subtract the x's and square it. That's what I did right there. And then you subtract the y's and square it. That's what I did right there. Add them up. And I got, a weird number, the square root of 89. That's a decimal. It's like 9.3 or so. So we're just going to leave it radical 89. That's the distance between those 2 points. Now let's talk about conics. So we had, first of all, the equation of a circle was always x squared plus y squared equals radius squared. Now this problem has an h and k in it, which is how I got the center. And then the square root of 25 was how I got the 5 there. Number 18, write the equation of an ellipse with a center. Now, I had to do a sketch here. So I did a very rough sketch where the center is over 2 down 5. The vertex is over 8 down 5. And then the foci, one of them, is over 6 down 5. Now, when you set up an equation of an ellipse, you need to know A and you need to know B, or B squared, because you need to plug that in the formula. Now, A is the distance from the vertex to the center. So 8 minus 2 was 6. Now, C is the distance from the center to the foci. Now, that's 4 when you subtract it. So how do we figure out B? Well, you have to use the formula that's in your notes, A squared minus B squared equals C squared when you're working with an ellipse. So 36 minus something squared is 16. B squared is 20. Now, when you set up the equation, since this is clearly a left-right ellipse, we need to put that big number, it's called the major axis number, the A squared, is going to go under the x, since this is a left-right equation. That means B squared is going to go under the y, and all of this equals 1, and you're done. So we didn't really use the C in our equation. Our C allowed us to figure out our B and our B squared so that we could create the equation. Number 19, state the coordinates of the foci. So we will need C on this one, right? We've got A squared. A squared is always the bigger one here, and B squared is the smaller one. So A squared and B squared, so that allows me to get A and B. I then use my formula to solve for C. And then since there's no h and k here, the center is just at 0, 0. And once again, this is a horizontal equation. The reason I know that is because the big number is under the x squared. So the foci is going, here's the center. The foci is going to be plus or minus from the center. So that's why I wrote that as my foci. All right, in number 20, I think I made a mistake. So I wanted to correct this here. The 12 should have been on the other side. I think that's what I meant to be, because on the 4a always comes from the first power side. So 4a is 12, so a would be 3 if that 12 is on the other side. I did go ahead and find the vertex by harvesting out the h and the k, so that's where I got that. Now, once you have a, this allows you to find the focus. Now, since the y is being squared, I know that this is a left-right equation, and since a came out to be positive, I know it's going to be to the right. So how much to the right, though? Well, that's where our focus is going to help. So we're going to go over 3 from the vertex and put a dot there, and then we're going to use that line segment called the latus rectum. We're going to go up 2a. So remember, this was 1a, so 2a would be 6. So that's why I went up 6 and I put a dot. And you go down 6 and put a dot. So the latus rectum has a length of 4 times a in total. So we go up 2a and down 2a, and that tells us exactly how wide that parabola is. All right, the last question has a minus sign in here. So we've done circles, ellipses, and we've done parabolas. This is the hyperbola shape, where it's almost like two parabolas, but they're not quite parabolas as we talked about in class. So the bigger number is your a squared. The bigger number is your a squared in when it comes to hyperbolas. I see the bigger number is under the y, so I'm going to call that my a squared. So since the bigger number is under the y, since the bigger number is 25, that's going to be my a. So a is going to be 5 when you take the square root. The smaller number is going to be your b here, so that's 2. Now, since a squared is under the y, that means my asymptotes are going to have the a on top. If the bigger number had been under the x, then it would have been reversed, and we would have actually put the b on the top. But we're going to put the a on the top because it's always the y number that goes on the top for your asymptotes. Remember, these are these have asymptotes, and then they have the two sections that are formed around the asymptotes. So all this question asked was the asymptotes, so there you have it. All right, hopefully you found this useful. All right, good luck on your exam.